Good morning, everyone. Thank you for coming today. My name is Zhang Haihan. I come from the University of Tsukuba. Our research topic is 3D dynamic scene generation for advanced driver assistance system by integrating RGB-D and aerial multi-view images. As is known to us, advanced driver assistance system has been widely used in daily life to help drivers avoid traffic accidents. By using AI detection, we can be noticed to escape from suffering many accidents. With the development of camera technology, vision-based solutions are becoming more and more available for vehicles. This is one of the most direct ways for autonomous vehicles to detect the surroundings. However, 2D information is limited in sensing the distance between your vehicle and the surrounding obstacles. It may cause danger if the distance is unknown. So, the 3D scene is normally applied in ADAS. Moreover, the movement of surrounding vehicles is one of the biggest problems for autonomous driving. So, a real-time visible 3D dynamic scene is necessary for vehicles to achieve the level 5 in autonomous driving. To summarize, we make a list of 4 main problems in large-scale dynamic dense scene generation. The dense point cloud contains a large amount of information, which leads to the difficulty in real-time processing. Besides, ordinary portable computers are not able to realize dense point clouds in large scenes due to the limitation of computing power. This causes problems for ADAS to show the current 3D scene for drivers. And second, the processing speed is inversely proportional to the accuracy and the mirroring range, and less information is available for real-time processing. However, it is not sufficient for the reconstruction of a distant scene in large-scale spaces. Nevertheless, and more information causes computing problems. And third, for 3D information obtained by multiple sensors, the scale of 3D information is different, which leads to the difficulty of unification. And fourth, due to the huge differences in information through different sensors, local processing can be difficult to register to the global map. There goes to my solution. I try to integrate the static and dynamic information together by making the best of the both generation methods. This is the overview of our whole system. It can be separated into 3 main sections: static point cloud generation, dynamic point cloud generation, and the integration of UAV and stereo camera. The static point cloud is generated from aerial multi-view images by using the UAV. First, the camera is calibrated to get the intrinsic parameters as camera model input. The aerial multi-view images and camera model are utilized as inputs in the SFM method to make a 3D reconstruction. However, all the parameter is calculated based on the pixel unit, so the scale of the output model is different from that of the real world. By choosing point cloud pairs from static point cloud to the ground truth manually, the scale can be matched to the reality. Then, in order to transform the static point cloud in the world coordinate system, the SAP registration method is applied. Static point cloud generation is the pre-processing of the whole system, which is prepared in advance for the dynamic scene. To generate the static point cloud from aerial multi-view images, we use the structure from motion method. This is the 3D reconstruction method. It allows of 4 main steps. We use the UAV to take enough aerial images and then track 2D features to estimate 3D geometry information. Then, bundle adjustment is applied to optimize the reconstruction model. Finally, feed the surface to finish the 3D reconstruction. The function of the SFM is to output the 3D scene geometry and camera motion at the same time. And this video shows the reconstruction model in our experiment. However, SFM is mainly based on estimation of feature points and BA optimization. These do not contain the scale information in the reality, so SFM does not follow the scale invariant feature transform, and all the output model size is based on pixel unit. To make the 3D model fit with the real-world objects, we propose this scale matching method. The scale parameter calculation is based on matching the point pairs of 2 point clouds. In this work, we extract the distance between the feature point pairs in the ground truth point cloud, and then manually select the same matching point pairs in the static point cloud. And G and P are the point coordinate in the 2 point cloud structures. So the scale parameter can be calculated as the equation. The coordinate information of the static model could be transformed into the real scale. Then we manually choose matching points to make a cross registration. This step aims to transform the static point cloud into the world coordinate system. I defined a world coordinate system as the ground truth data, which we will introduce later. And the ICP registration method is applied to make a fine registration. ICP is an optimization method which calculates the distance of the closest points, then minimize the difference between 2 point clouds by iterating the distance point to point. And this figure shows the original position of static point cloud and ground truth. Regard ground truth as the reference point cloud. The static point cloud coordinate can be transferred to the ground truth, which is the world coordinate system. Normally, the number of generated dense static point cloud can reach several million, which is difficult to be calculated on a portable computer. Therefore, proper downsampling method is necessary for this system. We utilize the normal space downsampling. This method is selected because its brackets are based on normal space so that it can protect more details on a complex surface such as trees and roads. And after downsampling, the point cloud number changed from 3 million to 50,000 points. The dynamic point cloud is generated by stereo images from a binocular camera. SGBM method is utilized to calculate the disparity map of the left image. Then we match the depth information into the RGB data pixel by pixel to get the 3D dense point cloud in one frame. Then make the video augmentary and segment the ground. We can get the dynamic moving objects. Dynamic point cloud is required to be updated frame by frame. In this case, we calculate the disparity map and then match it with RGB-D map to reconstruct the point cloud in one frame, and then update it frame by frame. To calculate the disparity map, we obtain the left and right image from a binocular stereo camera. Then we use the SGBM method to estimate the disparity value in every pixel block of left image. After camera calibration, we can get intrinsic parameter and extrinsic parameter. By using the geometry calculation, we can obtain the 3D point cloud by adding the depth information on left image. Then, to make a vehicle pose be tracked in real time, we use the Vero Augmentary by ORB SLAM tool to track the camera pose. This video shows the Vero Augmentary performance. To segment the obstacles with ground, we set up the height threshold on z-axis to remove the ground. We call it plane segmentation method. The segmented point cloud contains both static obstacles and dynamic obstacles. And trees, buildings, and moving vehicles information are all necessary to protect the drivers from the traffic accident. To integrate the 2-point clouds together, we need to initialize the pose of vehicle in the dynamic point cloud on the static point cloud. Here, we use the depth Fourier method to get a more accurate point cloud. Then, after noise removal and plane segmentation, we register the 2-point clouds together and obtain the transformation matrix. Then, after transformation, we can get a 3D dynamic scene with both static environment and dynamic objects together. To integrate the static point cloud and the dynamic point cloud together, more information with features are needed for point cloud registration. The 3D information is not stable if the point cloud is only based on a pair of stereo images. So we use the depth Fourier method to fuse many frames in the dynamic generation process together. The input is the point cloud in multiple frames by tracking the camera pose and registering the depth map. The dense map, which contains several frames of 3D information, can be generated, and all the methods are based on the TSDF fusion tool. This video shows the performance of the depth fusion, and the accuracy will be discussed in the evaluation experiments later. Camera localization method is mainly based on point cloud registration method. In this case, we use the FPFH descriptor. The input of FPFH is the point cloud with normal information, and the output is a histogram that can reflect the characteristics of the neighborhood around each point. Then, RunSec registration method is proposed to make cross registration of 2-point cloud, and ICP registration is for fine registration. After getting the transformation matrix, the dynamic point cloud can be transformed into the static point cloud. The experiment is based on 3 scenarios to simulate the real-world condition. And scenario 1 is to get the static dataset of the street. Scenario 2 is to simulate the pedestrian passing the road in front of a parking vehicle. And scenario 3 simulate the condition where 2 vehicles are passing by each other. And the dataset is obtained by using the 3 types of cameras. The static point cloud is reconstructed by using aerial multi-view images from DJI Mini UAV. The aerial multi-view images resolution is in Full HD with 60 frames per second. The dynamic point cloud is reconstructed by a Z stereo camera. This is a binocular camera with long-range 3D sensing. The measurable distance of the Z stereo camera is 25 meters, which is available for auto processing. To get reliable ground truth data, I utilized the Leica BRK360 camera. It contains a laser inside which is reliable to be the ground truth. And in this work, to make an accessible ground truth, we took the data in 4 different positions and then registered it together in Leica Synchron Register 360 manually. As we can see in the evaluation report, the bounded error is only 4 millimeters, which is available for the ground truth. To evaluate the accuracy and completeness of static point cloud, RMSD between the static point cloud and the ground truth is calculated. As we can see, the distance of more point pairs is less than 0.5 meters. The figure on the left shows the variation of cloud-to-cloud distance in a different area. Blue characterizes the good matching points, while yellow means the poor matching points. And the final RMSD of 2-point cloud is 0.0495 meters. This is a visualization of the dynamic point cloud. As we can see, these point clouds are performing in the real time. They show the performance in scenario 2 and scenario 3. However, the visible range is limited. To evaluate the registration result, I calculated the fitness, RMSD, and the number of corresponding point pairs. Fitness calculates the overlap area as the ratio of correspondence between interior points and the number of target points, which higher the better for the registration results. In the point cloud registration with plane segmentation, the fitness is smaller than the point cloud registration without the plane segmentation. However, the RMSD and corresponding pairs are much better than the point cloud registration without plane segmentation. And the blue point cloud is the static point cloud, while the yellow point cloud is the depth fusion dynamic point cloud. The static point cloud without plane segmentation can produce wrong registration result due to the local optimum problem while calculating the transformation matrix. And this is the video of the whole system. This video shows the scenario 2 and scenario 3. At the beginning of the point cloud transformation from the initial position to the registered position. And the green background is the static point cloud. As we can see in the video, the integration of the dynamic and static point cloud can be integrated together. And I also evaluated the time performance step by step as shown in table 2. And the system is tested on a laptop with Intel Core i7 processor with NVIDIA GeForce RTX 2070 GPU. And the cost is high in the static point cloud generation and the initialization parts. However, these processes are all generated in advance, so the whole system can be well performed in real time. To give a conclusion, this work proposed a method to generate the large-scale dynamic scene in real time for ADAS, and the dynamic objects of point cloud by using the aerial multi-view images from a UAV and the static environment point cloud from a stereo camera are calculated separately to reduce the computation cost. And each point cloud's accuracy is evaluated by calculating the histogram of the RMSD of point cloud pairs with the ground truth point cloud. And the entire system is tested on a portable computer, which provides that it is available for dynamic scene generation in real time in large-scale spaces. Thank you for listening.